Okay, this is my final FRQ test corrections, and on this one I scored an 8 out of 13. Okay, so number one, part 8 asks, in a clear, coherent paragraph, length response that may also contain figures and or equations, explain why the athlete's angular speed increases between figure 1 and figure 2, but decreases between figure 2 and figure 3. So I said that angular speed is how fast you're moving in a circle. Its displacement is theta. You can have angular speed but not move anywhere linearly. As the athlete does a rotation between figure 1 and 2, he gains angular speed because he is now also traveling in a circle as well as moving to the right. Between figure 2 and 3, the diver exits his rotation and travels straight down linearly. Because he is no longer rotating, he has no angular speed, and therefore his angular speed decreases. And this, the equation UG is equal to linear kinetic energy plus rotational kinetic energy can be used there. Okay, on this one I scored a 2 out of 5. The answer was in terms of angular momentum and inertia, which I didn't use. I still think my explanation worked, so that's why for the fourth and fifth point I got for explicitly addressing both intervals 1 and 2 and 2 to 3, which I did. And then I got the fifth point because I had a logical, consistent argument that addressed the required argument and followed the guidelines. So that's why I got the last 2 points. So if I were to redo this again, I would write something like, the athlete's angular speed increases between figure 1 and 2 and decreases between figure 2 and 3. And the evidence is because that angular momentum is conserved. So if the figure is no longer rotating in between figure 2 and 3, then they don't have as much angular momentum. Checking right. And this can also be used with the equation with O equals rotational velocity. So inertia is how easy it is for an object to spin, and let's see. And angular momentum is L. So if I becomes harder to, if I increases, meaning it's harder for the person to spin, then it'll have less angular momentum as well. Wait, it'll have the same angular momentum, but to counteract this, the angular velocity will decrease. So you can write, if this increases, O has to stay the same. So that means the angular velocity will have to decrease to balance out and to keep the same angular momentum. Part B. Is the rotational kinetic energy K2 rotational of the athlete in figure 2 greater than or less than or equal to rotational kinetic energy K1 rotational of the athlete in figure 1. Yeah, I got this one right. Said K2 rotational is greater than K1 rotational. And this is because, obviously, if you're going to be moving in a circle, you're going to have more kinetic rotational energy. Half inertia times angular velocity squared. You're going to have more angular velocity if you're going to be spinning in a circle, so you're going to have more kinetic rotational energy as well. Okay, so that one was this two. Okay, part C. Okay, there's no part C on this one. So second question is, okay, the cart one. Part A, based on the graph where the measurements started at the instant the cart was released. Justify your answer. So now I got plus 1 out of 1 on this one. No, cart already has velocity if started from rest. Cart should have 0 velocity. Okay, and then part B. Calculate the magnitude of the external force exerted on the system. Okay, yeah. So the external force will be gravity. So F equals ma is what I did. So if force is equal to mass, it gives the mass of the cars. Find it real quick. Okay. So I did like the triangle thing. We have to break up gravity. So okay, this is gravity going down there. Gotta break it up into that and that. So G. You're trying to find this theta. I'm trying to find this value here. Just call it X. So the first one's going to be 1 kilogram times 10 sine theta. We're using 10 for gravity. So G equals 10, so 10 sine theta. Right there. Opposite hypotenuse. So that's how you get the force exerted on car 1. And then car 2 is going to be 5 kilograms. The same gravity. So 10 sine theta. Car 2. Car 1. So yeah. Okay, I forgot to calculate the actual values from this because I don't know the theta. So I couldn't really calculate it this way. I would have had to use F equals momentum over time to get it. But I didn't, so that's why I missed out on 2 of the points. But I still got 2 for the setup. and for the correct setup, and for explaining how Newton's second law affects momentum. So this was 2 out of 4. Here's a part C. Okay, it says suppose the experiment is repeated with different carts so that the masses of cart plus magnet are 2 kg and 4 kg. Would your answer to part B be different with the new masses? So this one, I said I got 1 out of 2 on this one because my explanation was right, but my answer was wrong. So I said, yes, it would be different, but I did say that it would be 2 kilograms and 4 kilograms on the new masses, and those are obviously going to be equal. So yeah. And I said the force of gravity on cart 1 will increase while the force of gravity on cart 2 will decrease, and those will cancel out and ultimately be the same force after you're done.